Hello and welcome. Today we're going to go through some log base 2 examples. But before that, again, just a quick recap on what we learned so far. We learned about the logarithmic form and the exponential form. So let's say if you're a big fan of base 2, binary for life, then you will be familiar with these equations over here. 2 to the power of 4 is 16, to the power of 5 is 32, to the power of 6 is 64. So you can see a left-right relationship where on the left, we change the power from 4 to 5 to 6 and we get these numbers as a result. So that might trigger some of you to think, hey, wait, we are changing the left-hand side, 4, 5, and 6. What if I want to change the right-hand side? What if I don't want 16, 32, or 64? What if I had a very specific result in mind, like 48? Can you tell me 2 to what power is 48? And that, my friends, is what logarithms is designed to answer. Because if you look at the logarithmic form, right, you can see that when you write the log form, the exponent is the subject of the formula. Like if you want to know the answer, right, this is the answer. This is the exponent that you're looking for. All right, so I think we're all caught up and we are ready to play a simple game today. So over here, I have a number line showing the numbers from 1 to 100. I want you to think of any number between 1 to 100, and I am supposed to make guesses to guess what number you're thinking about. Okay, of course there are some rules to this game to make it a bit more fun, and that is whenever I make a guess, for example, if I say is the number 50, then you are supposed to answer me 3 things. Number 1, if the number you're thinking of is higher than 50, then you say, oh, 50 is too low. If the number you're thinking of is below 50, then you say, oh, 50 is too high. But if you're thinking of exactly 50, then you can tell me bingo. Yeah? So only 3 things you're supposed to tell me. Now, with that as the rules of the game, what do you think in the worst case scenario is the least number of guesses that I will need to single out the number you're thinking about? Okay, so this phrasing sounds a bit confusing. Let me just try and simplify it a little bit. If I'm unlucky enough to make no lucky guesses at all, right? By which guess would I be able to 100% confirm, say that this is the number that you're thinking about? I'm going to give you like time to think about this. You can pause the video if you need more time. And I'm going to go through the answer now. Okay, so there's one answer we can definitely cross out, and that's 100. Because if I'm unlucky enough to make 99 wrong guesses, then I would have eliminated 99 out of 100 numbers. Then there's only one number left. I don't even need to make the 100 guess to know what number you're thinking about. So does it mean the answer is 99? Probably not, because this game has rules. I can make use of these rules to come up with some strategy. Okay, so what is the strategy that I'm going to employ? Let's go back to the picture of the number line. Okay, so you can sort of imagine the numbers lined up very nicely in their number line. Okay, I'm going to call it like the solution space, because in this space of the number line, okay, the answer is somewhere inside there. Yeah, what strategy I'm going to employ is the name of the strategy I'm going to employ is called divide and conquer. Okay, I'm going to go straight for the middle number. So my first guess would be, is the number 50? Yeah, so you have to tell me 1 or 3 things, right? If you tell me bingo, which I think is very unlikely, because you should be smart enough to avoid numbers like 50. Okay, so then you have to tell me either it's too high. If it's too high, then that means the number you're thinking about is between 1 to 49. Or if it's too low, that means the number you're thinking about is between 51 to 100. Say if you say it's too low, then I can say that, oh, then you must be thinking about these, which means that I no longer need to guess numbers from 1 to 49. That is like almost 50 guesses that I have saved. I don't need to make those guesses. Okay, so once I know it's between 51 to 100, I can halve it down again, 75. Then you have to tell me too high or too low. If it's bingo, then that's no fun, right? So I want to know, right, how many times can I divide until I can isolate it down my solution space to just one single number? Because when I can isolate it down to one single number, that must be the correct guess, the number that you're thinking about. Yeah, so with that, do you know what is the least number of guesses needed? Well, instead of doing guess and check or listing down, we can actually solve this mathematically in 3 lines, sort of 3 lines, or maybe 4 lines. Let's look at this. So we can change the question to hey, I have a number 100, and if I keep dividing by 2, dividing by 2, dividing by 2, how many times do I need to divide by 2 so that my answer is 1? I have a solution space of 100. If I keep dividing by 2, dividing by 2, dividing by 2, how many divisions do I need to get 1? So that's the same as saying 100 divided by 2 to what power of n is going to give me 1. And for my final step, I'm going to multiply by 2 to the power n on both sides, and you're going to get this. Exactly what we talked about at the start of the video, and that is the kind of question that Logarithms is designed to answer. I have a very specific result in mind. Yeah, this is the result I want. Okay, I need to know what power, right? 2 to what power gives me that 100. So I need to use logarithms, right? So let's calculate using good old Python. Where's Python? No! Let's over here. Yes, there you go. I've typed this out previously, so we just need to run, and the answer is 6.64, which is about between 6 and 7. So I can sort of say that, oh, in the worst case scenario, I will need 7 guesses to get this right. So this is the correct answer, right? Which is pretty amazing if you think about it. Out of 100 things, you only need to guess 7 times, and you can correctly narrow it down to the one single thing that you're looking for. Pretty cool, right? Let's look at, say, a different question now. Very similar question, and that is, instead of 1 to 100, now we're going to look at 1 to 1000. We have 10 times the size of the solution space, right? 1 to 100 is like this. If you multiply it by 10 times, you have 1 to 1000. Again, think about any number between the 1 to 1000. In the worst case scenario, what is the least number of guesses that I will need? Is it still 7? Is it now 10? Or is it 70? Because now I have 10 times the space, right? Then I need 10 times the number of guesses to get it right? Or is it 1000? Which you should know by now is not the correct answer. So take some time to think about it, and we're going to go through the answer. So let's use good old Python, right? Let's just save ourselves from all the trouble. Just add one more 0 over here and run. Answer is 9.965. So 9.966. Yeah. So that means you only need 10 guesses. 10 guesses. Right? So think about it. That's pretty amazing. Like, I increased the size of the problem by 10. You think about it as, let's say, if we change the question to finding an object in your room, right? And then now I give you a room that's 10 times bigger with 10 times the number of objects. Can you find it in, say, 3 more seconds or 3 more minutes? Seems pretty impossible, right? But this is what's happening. This is really an amazing result, right? So if I have a space of 100, that is 7 guesses. 1000 is 10. If I continue on down, then 1 million will take about 19 to 20 guesses. 19 or 20 guesses. That's crazy if you think about it. 1 million things that you're looking for, the computer only needs 20 guesses to get it right. Yeah, and that is why computers are really, really good at crunching big numbers, you know, that humans take some time to do, right? Because they have this capability to halve things down really, really quickly. Okay, so I thought, yeah, this is a really, really great example, and I hope you enjoyed this. Now, I also know some of you have this burning question, like, okay, log-base 2 is cool and everything, but it is not on my calculator. What if I have an exam question that asks log-base 2? How am I going to calculate it? So this is where I want to draw the parallel to currency. Remember currency, right? Let's say you have a lot of US dollars and you are in Japan. You try to pay US dollars, but they just don't accept it. What do? You take your US dollars, you go to a money changer, and you change to the base currency of Japan, the Japanese yen. Likewise, if I gave you a question in log-base 2, you will actually have a change of base formula, like a money changer, right? To change it into either log-base 10 or natural log. So look out for that video if that is the question you're thinking about, and I guess I'll catch you on the flip-flop.